Welcome to video 6 on the TTb course. This video is from part 2 of the TTb course. In part 2, video 3 to video 10, we consider various techniques that form the foundation of reliable TT systems. In this video, we consider effective techniques for the design of tasks that are intended to be the same but different. The material in this video is based on Chapter 6 from the ERES2 book. If you have not yet read Chapter 6, I suggest you stop the video now, read the chapter, and then come back and view the video again. Let's consider an example. Suppose we have this task set running. Task C, as indicated, has a worst-case execution time shown in the white box above task C. Suppose the system runs. So suppose we have carefully determined the worst-case execution time of task C. We've measured it correctly. We've checked that we are comfortable that and we're confident that we've recorded that worst-case execution time correctly. Suppose we then run the system and find that task C exceeds the worst-case execution time that was determined at design time. Suppose we detect this at runtime. We'll look at techniques that we can detect such an overrun in a later video. For now, let's assume that this occurs. What should we then do? What should we do about the subsequent tasks that are due to run here? Remember, we've assumed that task C has a worst-case execution time that's been recorded accurately, so it shouldn't have exceeded this value. Something serious, we assume, has gone wrong, at least in task C. What should we do? One option is that we simply ignore this. And we say, okay, it's exceeded its execution time, let's just allow that to happen, and maybe we keep note of this fact and we record it in some form, in appropriate memory location or in flash memory, and we report this back the next time that our vehicle, for example, goes in for servicing, or we report it back using some other mechanism. We could do that. We could shut the system down, because we could assume that this is a serious situation and that we don't understand the cause of it, and if we don't understand the cause, we don't know whether we can run the system safely. If something has affected task C in this way, maybe it's a serious problem that's also going to affect another task. Maybe task C isn't itself directly safety critical or safety related, but maybe there are other tasks in the system that are, and if there's a problem with task C, maybe there are other problems with the other tasks in the system. The only thing we can do, we might decide, is to shut the whole system down. Another alternative, illustrated in this slide, is that we don't run task C again, but instead, in place of task C in the schedule, we run a backup task, a backup version of task C, shown as CB in this figure. If we do this, then clearly we'd like to try and ensure that whatever the underlying faults that gave rise to the failure of task C, task CB, our backup task, will not suffer from the same problems. So how can we create two tasks that operate in this way? How can we create two versions of a task that have similar but different behavior? How can we do this effectively? That's our focus here. So what we require is that task C and task CB should be diverse tasks. Such tasks are designed in such a way that the probability of common cause failures should be low. Again, the diverse tasks, you'll find a more complete definition of diverse tasks in Appendix 1 in the ERES2 book. In this video, we'll consider some of the challenges involved in creating effective diverse tasks in which we can be confident that the probability of common cause failures will be low. Overall, incorporating diversity in a design is generally considered a good thing in safety-related systems. So we could say, as a very rough model, that the higher the safety integrity level or ASIL level in our system, the greater the level of diversity we would like to have in our design. There are different forms that this kind of diversity can take. As an example, in ISO 26262, this standard describes what it calls software diversified redundancy, SDR. If you've got access to the standard, please take a look at ISO 26262 Part 5, Clause D.2.3.4. To paraphrase the standard, software diversified redundancy involves running two diverse tasks on a single processor, with comparisons carried out to check that the two tasks have generated the same results and action taken if the results differ. The techniques that we discuss in this video provide one way of achieving software diversified redundancy. Here's another example of the use of diverse tasks. If we're going to carry out ASIL decomposition, a process that we'll discuss in video 21, then we may need to run two sets of tasks that are demonstrably different on the same processor with a single scheduler and usually with some kind of external monitoring device. This is what we call a decompositor platform, and we'll look at this in more detail in video 21. So in this example, we'd have one task set, the task set A, running task A1, A2 and A3, and another task set B, composed of task B1, B2 and B3. These task sets are, we assume in this case, performing similar operations, but we want A1 and B1, for example, to be diverse tasks. That is, we want them to be performing similar activities but in a different way. We'll say more about the use of this kind of platform and the support for ASIL decomposition in video 21. In this video, we'll focus on the design of diverse tasks. As we'll see in later videos, effective design diversity can take several different forms. For example, the predictor mechanism that is used in the majority of safety-related TT designs, we'll discuss in video 19, involves the use of different representation of the task schedule for runtime monitoring. So we have one representation of the task schedule represented in the scheduler arrays and a separate independent representation of the task schedule that we use for runtime monitoring. This form of diversity is useful. Another example, in a duplicator HE design, also discussed in video 21, this involves two different processors, possibly from different manufacturers, working together to achieve the aims of the application. These are just two examples of other forms of design diversity that can be helpful in safety-related systems. Our focus in the present video is on creating diverse tasks. The traditional way a traditional way of producing two tasks that are different is to use n-version programming. This is still a source of confusion in my experience, and I want to talk briefly about what n-version programming is and why it doesn't generally work. So the question here is, how do we create two tasks that are the same but different? The key challenge here is that suppose we've created task X. We presumably did as good a job as we could with that. We used appropriate design and implementation approaches. We created task X in a manner that we would be comfortable that the task operated correctly. So we don't expect task X to suffer from any faults. If we expected that there would be faults with task X, we'd presumably have corrected those faults. So how can we try and create a backup task X or a diverse task X that doesn't suffer from the same problems as task X when we don't know what the problems are that we are trying to avoid? So if we've created one task and we've done as good a job as we can and we've created that task effectively, how can we create another task that's not the same as the original task and suffers from different problems and doesn't suffer from common cause failures? One way in which people have tried to achieve this is through what's called n-version programming. This involves creating a single specification for the system task and passing this to two independent teams. For example, we might have one team in Europe and another team in Singapore. Each team is expected to produce a version of the task to the best of their ability. It's very important to appreciate that we're not assuming that either task will be perfect. Instead, what we're trying to do is to find a way of creating two tasks that have different faults. That is, more formally, statistically uncorrelated faults. So that if we have a plane, we're 5 miles above the ground, task A in the plane fails, we replace that task with task A backup. We want to be confident that the task A backup will not suffer from the same faults as the original task that we have replaced. In that way, we have a better chance of getting our plane to perform a successful and safe landing. So how can we create task A and task A backup and ensure that they are different? N-version programming may look like a sensible idea. It looks like a design pattern, which is all that means. Design pattern simply encapsulates a successful, proven solution to a well-known design problem. In practice, I would suggest that n-version programming is an anti-pattern. That is, it looks like a good idea, but in practice it is not a good idea. In the mid-1980s, which is a long time ago, and yet a lot of people still think n-version programming is a good idea, John Knight and Nancy Levison set out to explore this issue in a study that has been much cited ever since then. So what they did was to test for statistical independence. They designed and executed an experiment in which 27 versions of a program were prepared independently from the same requirement specification by graduate and senior undergraduate students at 2 universities. The students tested the program themselves, and then each program was subjected to an acceptance procedure for the experiment consisting of 200 typical inputs. Operational usage of the programs was simulated by executing them on 1 million inputs that were generated according to a realistic operational profile for the application. Using a statistical hypothesis test, we concluded that the assumptions of independence of failures did not hold for our programs, and therefore that reliability improvement predictions using models based on this assumption may be unrealistically optimistic. In other words, what they found was that if you take same requirement specification and give it to two teams, you don't necessarily, there's no guarantee at all, that the resulting two different task implementations will be statistically independent. In other words, there's no guarantee that you'll see the two systems will not, the two tasks will not suffer from common cause failures. This study has proved to be influential, and it now appears to be, or should be, generally accepted that n-version programming is not an effective solution to the problems of creating two equivalent tasks that can be expected to fail in different ways. If you're still not convinced, some of the papers below you'll be able to find with a few minutes of Google search, and it may be worth reading those. But in general, if someone suggests using n-version programming, please be skeptical. So if we can't use n-version programming, how should we create diverse tasks? This is how I suggest you proceed. Start with an appropriate specification and produce a task to the best of your ability. Rather than doing this in a black box way, we should use a white box solution. So effectively, n-version programming says, have two teams, each create a task from the same specification, don't have the teams talk to one another, keep the teams apart, and just hope that the two tasks will be different. That doesn't generally work. So rather than doing that, we might have the same team produce the two tasks, but we do this in a white box way. So we deliberately try and focus on how one task was implemented and try and implement the other task in a different way. This may mean, for example, trying to ensure that we employ different hardware resources and different algorithms in the two tasks. Perhaps the use of some design patterns may help with this. We also know that coding errors are much less likely in short pieces of code, and we may therefore, if we're trying to build a backup task, keep the backup task very simple, in the expectation that this will be likely to improve reliability even if it results in reduced quality or performance. So this is sometimes called a limp home task. Another thing you need to think about when you're creating backup tasks is the potential need for dinit functions. The task modules that we've considered in previous videos have consisted of two main components: an init function that's called once before the task is added to the schedule, and a function, the task itself, that's released periodically by the schedule. If we remove a task from the schedule, we need to tidy up in order to avoid any side effects. For example, if task Z uses port pin 367 and we delete task Z from the schedule, we should include a dinit function in order to restore port pin 367 to its default configuration. If we don't do this, then some parts of the system may operate in an unexpected way. So when we design diverse tasks, the suggested starting point is to begin by ensuring that the hardware used in the two task designs is as different as possible. For example, suppose we have to produce a backup task for a design that generates analog outputs. If our original task employs a digital to analog converter, we might decide to base the backup task on a PWM output device. Having started from this different hardware base, we are likely to more easily generate a different software base too. It's not always possible to provide replacement hardware. In this In these circumstances, it may be more appropriate to consider alternative design options. For example, our design could have an advanced mode and several simple modes. The advanced mode might involve multiple sensors and a complex signal processing algorithm. Our simple modes may each involve a small subset of the sensor suite from the advanced mode. If a sensor fails in advanced mode, it may be possible to move the system into a simple mode in which the problematic sensor is not required. This can be an effective solution in many designs. So we have an advanced mode and a simple mode in the system. The original task might operate with multiple sensors. In the simpler mode, we use a smaller subset of the sensor suite, just the core sensors. Again, we're accepting there may be a reduction in the quality of service, but potentially an improvement in the overall safety of the system. That brings us to the end of this video. Before you watch the next video, please read Chapter 7 and Appendix 6 in the ERES 2 book. Thank you for watching this video.